Okay, it says this. Okay, so the topic is AI-based, which is top-down modeling, and I'm going to explain why it's called top-down modeling in a few minutes. AI-based top-down modeling, reservoir simulation, and reservoir modeling is the topic that I will be covering. And to get started, let me give you some ideas what this whole thing is all about. What are the requirements of AI-based reservoir models? First and foremost, it requires expertise in artificial intelligence, but just as much, it requires expertise in reservoir engineering. And of course, this reservoir engineering expertise is very, very important because this is AI-based reservoir simulation and modeling. If it was about drilling, then expertise in drilling was required. In other words, you need to have domain expertise in any topic that you are going to use AI to work with. However, you definitely need some expertise about AI. So let me go in a little bit of detail on that. Expertise in artificial intelligence, what does it include? And what is it usually when I teach this to my students or when I do short courses, what do I cover? I cover things that it's very, very important to become an expert. First and foremost, it's very important to know the history of artificial intelligence. Another one is it's very important to know the correct definition of AI. And the reason I'm saying that correct definition is that I came to the conclusion when I saw a recent, in March, actually, in JPT, Journal of Petroleum Technology from SPE. I'm a member of SPE for more than 40 years. Recently, things are a little different at SPE. But anyways, in March, JPT put an article from some people on. And in that article, one of the things that they did, they created it, or they mentioned the definition of artificial intelligence and a definition of machine learning. And to be very honest, I was shocked when I saw those definitions. Why? Because it was their definition of this technology. And what doesn't make sense is, don't you think that the definition of artificial intelligence should come from those who created it or those who use it in a different fashion that really have nothing to do with artificial intelligence? So, but anyway, so I'm going to show you the correct definition of AI. This is not, and machine learning, these are not my definitions. These are the definitions of this technology as it was created and generated a few decades ago. I mean, since 1986, actually. Then the next thing is the science and engineering application of artificial intelligence, because the application of AI in science and engineering is different from the application of AI in non-science and non-engineering issues, general intelligence. That's another problem that we have in our industry, unfortunately. Then modeling physics using artificial intelligence. And then what is the difference between artificial intelligence and traditional statistics? Because unfortunately, a lot of people think they are the same thing. They're not. What confuses people is because statistics is also data-driven, no doubt about that. And AI right now, to a very large extent, is all data-driven. So just because they're data-driven, it doesn't mean they use the data and they drive it and they deal with it in the same fashion in both cases of statistics and AI. Actually, they're quite different from each other, the way they deal with the data. And that's another thing that I go to in a lot of detail and explain, but I'm not sure how much of that can be explained here. But if you have questions, please ask and I will try to explain it. Another very, very important issue, which I'm going to cover in this presentation, is kind of ethics of artificial intelligence. And this is something that came up in a few years ago by US Department of Defense. through some of the issues that happened in the United States when AI was used. And of course, it was done for non-engineering application of it. And when I did research and learn about it, it was absolutely fantastic to learn about what ethics of artificial intelligence is. And then I learned how it can be applied to engineering application of artificial intelligence. And that's why a lot of, unfortunately, current there are people who use who go through ethics, undo the ethics of artificial intelligence to solve engineering related problem. And I will explain that as well. It's very important for everyone to learn about that. And finally, it's explainable AI. That also came up in the United States in a big time to find out how can you explain what AI model, when AI uses the data to build a model, how can you learn more how AI did that and how different application and parameters apply in a different fashion. Anyways, so that's the expertise of AI. But then there are expertise of reservoir engineering. Why? Because we're dealing with, in this workshop, we're dealing with application of AI in reservoir modeling and using AI to build the reservoir model. And I explained how different that is from what we have been doing reservoir modeling in the past 80 years. And in the past 25 years, I've been teaching it at the university to kids how to do numerical reservoir simulation. And the question is, I'm not saying it's a bad thing because I've been teaching it, I still do. However, there's a difference between how we use AI to do reservoir modeling versus we do what we have been doing in the past 80 years in reservoir simulation, numerical reservoir simulation. Nevertheless, for AI-based reservoir model, expertise in reservoir engineering is absolutely required. We need to know the fluid flow in porous media is a function of space and time, and know a lot of details about that fluid flow reservoir model versus well-based modeling, as you are very well aware, because when you do well-based modeling, you deal with a single well. When you do reservoir modeling, you do it with the entire field and as many injectors and producers that are working. Then full field reservoir modeling versus decline curve analysis. That's another thing that we actually teach, and we've been doing decline curve analysis since 1960. But again, full field reservoirs, numerical reservoir simulation, or any kind of reservoir modeling is very, very, very different from decline curve analysis. And the importance of geology in reservoir modeling, because as you saw in the first one, reservoir fluid flow in porous media is a function of both space and time. And the geology part of it has to do with space, which has to do with well logs, it has to do with cores and seismic and all that detail. So in other words, you have to be very good reservoir engineers to be able to use the AI-based reservoir modeling. So in the items that I mentioned to you, I'm going to cover these three items. I'm going to give you a correct definition of AI and machine learning, how physics is modeled using AI, and ethics of artificial intelligence. The other topics I cannot cover because of the amount of time we have here. And even those I have to be very short and quick. And after that, I'm going to give you reservoir simulation and modeling, AI-based issue, top-down modeling. And I'm going to tell you how different and why it's different with numerical reservoir simulation that we have been using it for past 80 years. Then I'm going to talk about intelligent data patching, given the fact that when you deal with historical data, there's always some data missing, how you have to handle that. And then we talk about geoanalytics. It's a technology that we have developed recently. It's AI-based geological modeling, which you'll see there's a bit of difference between that and how geological model for reservoir engineering has been done in the past 80 years. And then the AI-based reservoir model is a purely automated history matching, and you need very little interaction with it. You need it prior to the history matching and after history matching, and the history matching does its own. I'll show it to you. And we do blind validation, something that these days nobody does it in numerical reservoir simulation, and I explain that as well. Then I'm going to show you AI-based dynamic production allocation, because we do production allocation using KH, permeability and thickness of each layer when you want to find out how much production comes from each layer, because your reservoir usually have multi-layer. And then finally, I'm going to show you OpEx and CapEx optimization. That's what we all do when we do reservoirs. We do reservoir simulation and modeling in the past 80 years. Why? Because we want to optimize production during and optimize identification of where to drill the next well. And I'm going to actually show that to you through actual case studies that we have done for many companies and results. So with that, let's talk about correct definition of artificial intelligence and machine learning. First and foremost, let me tell you one thing, and that is AI is a revolution right now in our technology, in our world. If you go back about 70,000 years ago, humans, sapien, who we are today, they came from East Africa to what today is called Middle East and Europe. And that was the cognitive revolution. Why was a cognitive revolution? Because prior to Homo sapiens, others who came in were Homo erectus and Homo neanderthals. And they also went to different places in the world, but none of them, I mean, actually, Neanderthals came to Europe and Middle East about 100,000 years before Homo sapiens, and Homo erectus actually came before 70,000 years prior to Neanderthals. But none of them moved away from hunter-gatherer during all that time. But 70,000 years ago, that us, Homo sapiens, came to Eastern and Middle East and Europe. What we did after about 58, 60,000 years, we changed a lot of things that the others didn't. What we did was we had an agricultural revolution, which changed a lot what used to be gather. And after that, in about 10,000 years after that, 11,000 after that, we had an industrial revolution in mid-18th, which completely changed a lot of things. And that's why we are so different from others. And that's why we are Homo sapiens and who we are. However, now in mid-80s, two different technologies started. One is artificial intelligence, the other one is biotech. And these two are a new revolution that's going to change everything in the next few decades in our world. And the biotech, of course, is CRISPR that was developed in 1987. And in 2002, the CRISPR-Cas9 came in, and soon that's going to change a lot. If you haven't followed that, you should, and it gives you a lot of information. If you have any question, I'll be happy to answer. So in that context, what is the definition of AI and machine learning in a nutshell, in a very short one? Again, these are not my definition, these are the real definition of those who created this technology. First and foremost, this is the definition of artificial intelligence. Artificial intelligence is the technology that simulates human intelligence. How does it do that? It does it through mimicking human brain. So it all has to do with human brain, that our intelligence comes from our brain. And AI actually simulate this process in order to analyze, in order to model, and in order to make decisions. That's what AI is. What is machine learning? Machine learning are algorithms that create AI. Machine learning is the science of making computers to act without being explicitly programmed. folks, for those of you who have done numerical reservoir simulation or any kind of coding of computers to do something that they have done in traditional engineering and science for us, what does it do? We, in our codes, we tell computers to explicitly do exactly what we want them to do. Every single thing. And so computers do exactly detailed everything that we tell them. Is that the same in machine learning? No. Is that the same in AI? No. What is machine learning? Machine learning works through using open computer algorithm, not detailed, explicit computer algorithms. It's an open computer algorithm that works with all sorts of data, and it learns from the data. So the algorithm of machine learning is an algorithm that learns from the data. So data could be about many different things, right? But the same algorithm learned from it, and that's why it's called machine learning. And your job is to teach the machine using data, because that's what learning is. Learning comes from teaching. And that's why you have to be domain experts. I'm talking about engineering application. So with that, I like to let you know actually that machine learning algorithms are used for development of artificial intelligence. And in the past 31 years that I've been working on it in petroleum engineering, there are 3 machine learning algorithms that I have been using to work and to deal with artificial intelligence. One is artificial neural network. And these artificial neural network its job is mimicking life and nature through human brain's information processing. The other one algorithm is fuzzy set theory. That mimics life and nature through human brain logic, because the logic that you and I make as humans is very different from the logic that Aristotelian logic provides that it's used in traditional engineering. Aristotelian logic has 2 values, yes, no, black, white, 0, 1, up, down, right? Does our brain, does its logic in 2 value? No. It uses infinite number of values. It's not 0 and 1. It's every number between 0 and 1, which is infinite numbers, right? So that's what fuzzy set theory does rather than traditional engineering. And finally, the third algorithm is genetic algorithm, which is optimizing through a natural selection. And these are the things I go in a lot of detail when I teach the course, but right now I just give you an idea what to cover. So with that, let's quickly talk about modeling physics using artificial intelligence. So physical phenomena is solved using mathematical equation. This is what we have been doing as engineers in the past several centuries. That's what I showed you as Industrial Revolution that took place in 17th, 18th century. So I'm going to give you an example. Think about these rocket trajectory, right? When one country tries to hit another country with a rocket, for example, the war that's going on right now in, let's say, different places in the world, for example, Russia and Ukraine, right? If Russia wants to hit a rocket to identify exactly where in Ukraine is going to come down, how would it do that? That trajectory of the rocket that we know exactly where it comes from, where it kicked from, and where it comes down, because you identify where it should come down, right? When that happens, how do we do that? That's a very, not very complex, but reasonable mathematical equation. The range, to identify where it's going to come down, has to do with initial velocity with 0 and with the data that, that identifies where, how much away from field is going to be. So if you know theta and you know V0, then you can find out where it comes down. Or if you know exactly where it comes down, and we know the gravity, then you have to change the values of theta and initial velocity and the angle to do it, right? So this is something we know, that this is the mathematical equation. It's a physical phenomenon. That's very, very simple, right? Okay, so the question is this: can human brain address physical phenomena? This is a good example that I just gave you. Throwing something to be caught by another person. In the US, the football is when one person who is have the ball throws it and another person runs and catches it, right? And the question is, this is exactly like what I showed you in the rocket trajectory, and the fact that there is a mathematical equation identifies where this coming down, and you have to go and catch it. So the question that comes down is, this is the engineering approach to know how to catch the ball, right? So the question that I have for you, I want you to think about it for a second, is when somebody does that, if I throw something at you and you catch it, the question is, does your brain actually goes through at this particular mathematical equation, and it solves it, and it identifies where it's going to come down, and then based on that, your brain tells your muscles, your hand and your foot, where to go to catch it? That's the question. Does it? It's obvious. The answer is no. But the question is, can human brain address the physical phenomenon? The answer is yes, it can address it. But how? Does it address it through mathematical equation? No, it doesn't do it through mathematical equation. So modeling physics using data rather than mathematical equation is what we're dealing with. So then if what I just showed you right here, we know that our brain doesn't create a mathematical equation and solve it to identify where to catch it. So the question is, then, how does human brain solve physics-based problems? Our human brain solves physics-based problem by observation, by learning, by trial and error. It actually uses actual data. So what you can see right now is a person, even a child can do that. Take this thing and carry it on its hand. And this can also be done mathematically, of course, but it's very, very, very complex to do it. The other one I showed you was very simple. Actual data used by human brain is uncertain. It's full of noise. So when something is thrown at you to catch, your brain knows exactly the initial velocity or the angle? No, it knows how fast or where the angle is, but it's uncertain, those data, and it's noisy, but still our brain can deal with it. So since AI mimics human brain, then can it use actual data, which is uncertain and noisy, to solve physics-based problem? The answer is absolutely yes, because that's what it's doing. It's trying to do exactly what our brain does. That's the key about solving physics using AI, using it without mathematical equation. Once proven that physics can be modeled by AI and machine learning using data, what does that mean? Well, it means that AI-based model of physical phenomena can be developed using actual, real, measured data, unlike what we've been doing. When we do physical phenomena, we solve it with mathematical equation. This is how AI is different. AI doesn't use mathematical equation to solve physical phenomena. It only uses the data through machine learning algorithm. This would serve as an alternative difference to traditional modeling of physical phenomena. So this is the key, folks. You can solve physical phenomena using AI through mimicking the human brain. And that is different from what we traditionally be doing it through mathematical equation. So with that, again, there's a lot more detail can go to, but the time doesn't allow. Let me go ahead and tell you some buzzwords, some problems that we have. I have a question for you. Look at this item, and let's assume somebody tells you, some company tells you that our company can make a master physicist, and it can do it only in 1 month. When you hear that, what do you think? What if another company says we can create a master chemical engineer in just 1 month? We can make a master mechanical engineer in 1 month. We can create a master in petroleum engineer in just one. Does that make sense? By the way, nobody has ever said that. I just made this up. Why did I make this up? Because I wanted to ask you, if somebody says that, would it make any sense to you? Obviously not, right? Because you became a master expert in petroleum engineer in 1 month? No, you went to classes, you got your high school diploma, then you went to university, you got a bachelor's degree, took you 4 years, then you got a master's degree, got you 2 years, some of you got your PhD, worked for companies but this guy tells you they can do it in 1 month. When they say that, what do you think? You think that they have no idea what they're talking about, or it's all nonsense, right? This is not real, what I just showed you. Nobody ever says that. No company has ever done such marketing. Now, next, I'm going to show you something which is exactly happening everywhere right now. They say they can make a master data science in just 1 month. I'm not telling you which company does that, but it's true. This is a real marketing advertisement. That's the problem with AI in engineering, because people think it's so easy. It's not. It's just as tough. It's just as strong as your domain expertise. So in order to solve petroleum engineering related problem using AI, yes, you first and foremost must be a petroleum engineer expert, but you have to become an expert in AI. And unfortunately, a lot of companies, service companies in our industry, vendors in our industry, that tell you that they know AI and they're going to solve AI. I'm not saying they're lying, but they have no idea what AI is. This is what they think. Anyways, one last thing before I go to thing is ethics of artificial intelligence, AI ethics. What is that? I'm going to show it very little to you, but hopefully that gives you something to go ahead and learn more about it. Ethics of artificial intelligence becomes a research topic due to creation of racism and sexism using artificial intelligence in the past decade. It happened in the United States. Companies such as IBM, Google, Amazon, and many others, they actually did that, but they did it unintentionally. They did that because they want to do that. No, they learned later on. But unintentionally, they developed racism and sexism using AI models and have made effort when that happened, and they did it unintentionally. They did research. Why did that happen? And a lot of others started doing research because it came up with US Department of Energy, US Department of Defense. And to find out why that happens. One solution for addressing bias such as racism and sexism, is to create documentation or spend a lot of time on the data that is used to train the AI system. Massachusetts Institute of Technology, MIT University, reviewed AI ethics. They have created a whole situation a whole department to do AI ethics research. What I'm showing you is what MIT has generated. It says that the problem of bias, racism, sexism, or creating what you want into machine learning. So the problem of bias in machine learning is likely to become more significant as the technology spread to critical areas like medicine, like law, and I added this word, like engineering. And as more people without deep technical understanding or domain expertise are tasked with deploying it. So if you don't know what you're doing, then you can create that problem. Furthermore, they say, MIT says, some experts warn that algorithmic bias is already pervasive in many industries. Folks, one of the biggest one is now engineering. I'm going to explain it to you in petroleum engineering. And that almost no one is making an effort to identify whether it's correct or not. That's unfortunately happening in our industry, petroleum industry. Also, MIT says, Google's AI chief says, forget Elon Musk's killer robot and worry about bias in AI system instead. That's what the problem is, that bias, rather than what Elon Musk says. And anyways, so how is that happened, this AI ethics problem in petroleum engineering? This is what they call hybrid model. That's an AI ethics, engineering AI ethics. Why? Let me explain it to you exactly as I showed to you racism and sexism. I have written all article on that. And if you're interested, I can send it to you. AI-based modeling of physics is purely based on fact and reality through actual measurement. Traditional physics-based modeling includes some of the following items through mathematical equation. Traditionally, we can include assumption, we can include interpretation, simplification, preconceived notion, and biases. By including data from mathematical equation to actual measurements, you are telling AI what to do. So hybrid model is when people try to solve a problem with actual data, measured data, and they can't. Then what do? Sometimes they don't tell you why they are doing that, but that's mainly the reason. What they do is you use mathematical equation and they generate a lot of data from the mathematical equation and they hybrid it, combine it with the actual data. That's why they call it hybrid model. Then they can solve the problem. Why? Because mathematical equation already provides you a correlation, a process, and when you combine that to the actual data to do AI-based model, you are telling AI what to do. That's the bias. So let me give you an example. This, what you're looking at, is actual data in an offshore field in Southeast Asia, one of the projects that we have done. In these three, what you see on the y-axis is oil production. In x-axis, this is gas lift, this is completion, this is porosity, and oil production versus porosity, completion, and gas lift. This is for conventional. For unconventional, it's actual data from Marcellus Shale in Pennsylvania. And this is what you see is gas production versus lateral length, stages, and property. Right? Imagine that I showed you that data to see what the actual data looks like. There is no pattern, as you can see here. It's very non-pattern, and you have to mathematical equation doesn't generate that. So if that is, I'll give you an example. If that is the data, the objective is to use the data to develop an AI-based model. If you are successful, then you're done. However, if your AI approach does not work, what would you do? Well, in hybrid models, you know what they do? They use a mathematical equation and they generate more data and they combine it with the actual data that you have. And they do more and more and more. And then there you go. They come up with a solution. However, let's say Schlumberger did this one But another service company using the same data, using the same approach, but it used different mathematical equation, and it gives you this, right? And it gives you a different result. So literally for the same data from actual data that you have, using different mathematical equation, you are telling using hybrid model, you're telling AI what to do. And it has nothing to do with reality. Okay, with that, I'm done. Let's talk about the AI-based top-down modeling, given all that information I gave you. What is the difference between AI-based top-down modeling versus numerical bottom-up reservoir modeling? I'm going to explain top-down, bottom-up to make sense. First and foremost, the traditional numerical reservoir simulation that I've been teaching it for 25 years, and you probably all have taken the course, I still teach it. It's a very good technology. However, there is issues associated with it. It includes assumption, it includes simplification, it includes interpretation, and it provides the opportunity to include preconceived notion and biases. If you want to do that, you can do that. How about AI-based reservoir simulation? It is purely fact-based, and it's all about reality. Actual field measurement determines the quality of the reservoir model. In traditional numerical simulation, you start from the bottom. You start from the geological model. It's the reservoir 10,000 feet under the ground, at the bottom. And then you match the history of the production. Production, where do you see it? On top, on the surface. So that's why you go from bottom to the top. How about AI-based reservoir simulation? You do exactly the opposite. You start from production history. You start with everything that happens on the surface. How much oil, gas, water is produced? What is your choke setting? What is wellhead pressure? What is flow line pressure? Everything that happens on the surface that you can actually measure. And then by the time you finish it, you generate a AI-based geological model in the bottom. So that's the difference. You start from the top to go to the bottom, and in traditional, we do it other way around. We start from the bottom, going to top. Okay, so I'm going to explain that. AI-based reservoir modeling takes an opposite approach when compared with traditional numerical reservoir simulation. Imagine this is a field, and these are the wells that has been drilled from the top. And these are the well bores, and these are the completions at the reservoir. The bottom is the reservoir. So this is the top, and this is the bottom. When you go from bottom, first you model that you, as a reservoir engineer, you ask the geological people to generate a model geological formation, and then you use that in order to do history matching of what you see on the top. So bottom-up modeling starts with space and then brings in the time through mathematical equation. As you know, fluid flow in space and time. In AI, you use the measured historical production that you measure at the top, and then you history match it in order to find out what's happening down there. So top-down modeling starts with time, then brings in space through field measurement. You see the opposite of to each other. One more thing, when you use bottom-up numerical reservoir simulation, you need flowing bottom hole pressure. And if you know, I'm sure you do, we hardly have that measurement. That's why we, during the history matching, liquid or oil production becomes input to calculate flowing bottom hole pressure to history match. That doesn't happen in AI. Since we know that flowing bottom hole pressure is hardly available, we don't use it. What do we use? We use flow line pressure. We use choke setting. We use wellhead pressure, temperature, everything that happens in the surface, as well as how much liquid has been produced. One more thing, remember this is the field, this was the reservoir characteristics. This is the reservoir where the characteristics is that we need to know. And this is the well we drilled. And this is the well bore. And actually we'll drill it all the way to the reservoir. And then we, in the completion, we start identifying where it is, right? But then we use this. What is this? This is the fluid production that comes to the surface, and that is the operational condition. We use these in order to build the model. So the definition of TDM, top-down modeling, is an AI-based, comprehensive, empirical, full-field reservoir simulation. It develops solely based on field measurements, well trajectory, and all of these details. TDM is fast and accurate reservoir model that is validated using blind history matching, and it's autonomously updated, and it's real-time reservoir modeling. As you saw, top-down modeling doesn't only use the reservoir, it uses the reservoir and the wellbore and what's on the top. So operational conditions such as chokes setting, wellhead pressure, wellhead temperature, flow line pressure, flow line temperature, these are all input in the AI-based top-down modeling. And oil production is the main output of it. It's not an input like numerical reservoir simulation at the beginning during history matching. In top-down model, these dynamic variables are simultaneously history matched. We history match simultaneously at the same time for every single well in the entire reservoir, not single well. Oil, gas, water, reservoir pressure, and water saturation in TDM. Others do it differently. So how do? We use all the field measurement, static data, dynamic data. We take them and we do data quality and control, quality control and quality assurance. It takes a lot of time. Actually, when you do a project, more than 50% is dealing with this data from a domain expertise to understand exactly what's happening. Then we take that data to intelligent data patching. I'm going to show you in a minute. We do data dynamic conductivity mapping. I'll show you that identifies how. So intelligent data patching take care of any data that's missing without mathematical equation. Dynamic conductivity mapping identifies communication between all the wells that are producing and injecting. It tells you what the dynamic conductivity is between all the wells. And then we do, those provide you geoanalytics, which is geological model using AI. We call all of that spatial temporal data set that has to do with space and time for reservoir simulation. Then we took that to do automatic history matching. Automatic history matching uses all of that to provide you with oil production, gas production, water production, reservoir pressure, and water saturation for every single well at every time step that you deal with. And if it's not successful, then we go back to the data, find out what did we do that was not correct, and change it and correct it until we get a good history match. And once the history match is correct and blind validation is done correctly, then we can find out that it's production. We do production forecasting. We can do sensitivity analysis. We can do everything that people correctly do in reservoir management. We do it far more successfully, and I'll show you examples. First and foremost, what is intelligent data matching? So how to handle missing data, because always there is some missing data. We do not use mathematical equation. You should not use mathematical equation, as I explained in AI ethics to you. So data from mature fields. One of the major characteristics of mature field is the fact that always some static or dynamic data is missing. There are wells that are completely missing data. There are wells that partially missing data, and there are wells that have all the data, not missing at all in a history, right? So I'll give you an example. This is the data. Let's say we're looking at the wellhead pressure. This is a well that has no missing data. As you can see, on the top you have liquid and gas, and x-axis is data, and at the bottom you have wellhead pressure versus date. So as you can see, every wellhead pressure is available for every production that you have. So there's nothing missing. However, in this one part, it's partially missing. Same, it's another field. You have liquid and gas production on the top, you have wellhead pressure on the bottom. But this area, you have the production, but you don't have wellhead pressure. Here you have the production, you don't have wellhead pressure, and so forth. This is partially missing. This one misses completely wellhead pressure. You see the production, but you have no wellhead pressure. How do you handle it? First, for every single well, you say, okay, this is the well, and these are the data, the entire from beginning to the end of its production from 1979 to 2020. This is for a project that we have done. And these date for this particular well's production, what you see in green, you have that means oil production is available, wellhead pressure is available. When you see red, that means oil production is available, but we are missing wellhead pressure. And wherever you see black, that means there is no oil production that was shutting. So you don't need wellhead pressure for that. When you do that, so this, when you're looking at this particular well, 20% of the data of wellhead pressure is missing. How do you handle it? This is for the entire field. You can see for, these are all the number of wells, as you can see. And for each well, this one is missing 15%, this one missing 11%, this one is missing 100%, and so forth. Okay, when we want to do that using AI, we use all the existing data to generate the data that's missing. As an example, what we do, we take one of the fields, this is a field actually in Southeast Asia, and we use one well right here that it has the production and it has the actual data, actual wellhead pressure, but we do not use that to build the model. We put that aside out. We build the model using AI to find out if we can find out if we are missing wellhead pressure, can we generate it? And then once to come to a conclusion, to make sure that what we're doing is correct, then we come and apply it to this particular well that we didn't use the wellhead pressure to build the model, to do this intelligent data patching. We just did it to find out if it works. And this is IDP, intelligent data patching of wellhead pressure. And as you can see, it works very, very well with actual data. This is for another well that we did, blind validation. So when this happens, then you can trust the data that identifies. Okay, so we have only 10 minutes left. So instead of showing you the geoanalytics and all others, given the fact the time doesn't allow, let me go ahead and give you some good examples of the results of the top-down modeling. I'm going to go here to the end. What you're looking at is OPEX and CAPEX optimization. These are actual projects that we have done. So what is OPEX optimization? Operational characterization optimization, water injection optimization, completion in new reservoir formation optimization, and reopening a certain abandoned wells, if that is possible. These are OPEX. And in CAPEX is identification of optimum infill location. And I'm going to give you an example of all this for in infill location for production or for injection. Here's an example. This example is from ADNOC. The name of the field is Buhasa. We did this for them several years ago. And then they came back and told us, okay, 5 years after we did the project, they came to us and they said, since 5 years ago that you did this for us, we have generated 23 new wells. And in these new wells, we know when we drilled them, we knew what the pressure and the saturation was, but we're not going to tell you what they were. Go and use the TDM model that you generated for us 5 years ago. We just give you the location of these 23 wells. And I want you to, they wanted to give us a new project, by the way, on TDM, but they wanted to test this to see, give us a new project or not. So they said, we give you these 23 well, and we want you to tell us what, when we drilled these 23 well at each layer, what was the pressure of the reservoir? Can you tell us? What was the saturation, water saturation of the reservoir? Can you tell us? So we called it stress test predicting reservoir pressure for 23 wells 5 years after the completion of TDM. So we went back to the TDM that we developed 5 years ago and took these 23 wells that was drilled in 5 different layers in this Buhasa, and these were that gave us the location, and we gave them the pressure, and then they compared it with the actual, and they let us know. We found out that 35% of these 23 wells, the reservoir pressure that we provided was more than 95% accurate. 26% of them were between 90 to 95% accurate. 30% of these wells were 8. So literally the whole thing that we gave them, more than 90% of the TDM prediction of the pressure was more than 80% accurate. We did the same thing for the water saturation. The result was 70% of the TDM predictions were more than 80% accurate. This is the results. This is another one that we did. They wanted the choke setting optimization, how to change the choke setting. This is in Caspian Sea. Another project that we did for another company, and they said 3 wells choke setting was modified based on TDM for the recommendation. These are the 3 wells that they were told us how it is, and I cannot show you the platform or the well name of the zone, but they had it originally in high pressure, and we give it to low pressure the wellhead system, and we told them that it's going to enhance the production. And when we did it for actually a lot of wells. They did only 3 of them, and they said that they created 189 barrels per day extra based on what we told them. Production, but this is we actually did for all of them. They tested. We did about 15 different wells. 2 out of 15 were not correct, but 13 were correct. 87% of what we told them was correct when they tested it. This is history matching. This is actual data, and this is what TDM forecasted. Sorry, this is what TDM forecasted, and this is when they measured later, compared it with what TDM forecast. This is for one well, this is for another well, this is for another well, and this is for another well. This is the last one. So let me tell you one more thing. This is about well location. The manager of a company that we did a TDM for, in ATCE, Annual Technical Conference of Society of Petroleum Engineers, he was part of a panelist, and he made a presentation on AI that they said they were used in order to identify where to drill a well, and in that context, what would be the results of production of the well that they did. So what he did, he provided this, what I'm showing you right now, he actually presented it in end of September of 2020 for ATCE that was virtual. And I watched it actually. And when he did that, I knew that we did the AI-based model for them because I knew that person, that manager. I asked him, since you presented it to SB, is it okay for me to present it or give me? I didn't really know that. We just told them where to drill. They had not told us when did they drill and what was the result, but then they presented it. So I asked them to give me the data, and I presented it. Since they had already presented, he allowed, and we did that. This is what I'm going to show you. So this is the field, and here is the 4 wells that he compared them with each other. These 4 wells are these 4, 1, 2, 3, and 4. 3 of them, 198, 195, 178. These 3 were developed or identified by numerical reservoir simulation with the largest service company we all know. I just told you the name. And they told them where to drill, they drilled, right? And I show you when. But this one was through TDM that we told them where to drill, right? And the key is now we give you the results based on what they presented. The average production rate of the first 6 months for these 4 wells, we compare them together. First and foremost, what they said that the data all was measured in April 2020. This numerical simulation well, 178, was identified by numerical simulation, drilled in 2013. So by the time they were doing the calculation, it was 86 months since this well was drilled. And the first 6 months that this numerical simulation identification of the well was produced, it was producing 1,552 barrels per day, this particular well, in the first 6 months. This particular well was developed or drilled and identified by numerical simulation location. They drilled it in November 2014. So by the day they did the measurement, it was 65 months. This well was produced, on the first 6 months, it was producing 1,331 barrels per day, average. The third one that they compared by numerical reservoir simulation was drilled in February 2015, which is 62 months from this time. And it had produced an average of 1,298 barrels per day in the first 6 months. This is the TDM AI-based model that we told them in 2017. Actually, we did the project for them. So they drilled it in June 2018, and it's 22 months from the April 2020 that they did. Look how much it produced in the first 6 months, 2,156. That's the comparison of identifying where to drill the new well through geological AI-based. And he showed that then when we got the data from them, we actually calculated the whole thing. We said, okay, in April 2020, this particular well that we said where to drill was already drilled for 22 months. Let's compare the 22 months, first 22 months of this well versus the first 22 months of other 3 wells. When we did that, instead of 6 months, this is 22 months average. Daily average of the 22 months was 1,677, 1,316, and for the third one, 1,400. The TDM well, we told them where to drill. The 22 months, its average was 2,056. So it's 1 hour. I'm going to stop doing it. There's a lot more I can show you, to be honest with you, but it's very, very hard to do that. I'm going to stop since we were 1 hour to explain everything, and I'm going to answer any questions.